Greetings to all the listeners. I'm Rupam Gumber. Today I gonna present on the topic History of Ancient Mathematics. Index. Why Ancient Mathematics? Introduction. Egyptian Mathematics, Mesopotamian Mathematics, Greek Mathematics, Numeral System, Arithmetic Operators, Geometry, Hindu Arabic Mathematics, Invention of Negative Numbers, Invention of Zero, Number Line, Development of Algebra, Roots of Equation. Why are we discussing about history of mathematics? There are many excellent reasons to study the history of mathematics. It helps students develop a deeper understanding of the mathematics they had already studied by seeing how it was developed over time and in various places. It encourages creative and flexible thinking by allowing students to see historical evidence that there are different and perfectly valid ways to view concepts and to carry out computations. Introduction. Mathematics, the science of structure, order, and relation that has evolved from elemental practices of counting, measuring, and describing the shapes of objects. It deals with logical reasoning and quantitative calculation, and its development has involved an increasing degree of idealization and abstraction of its subject matter. Since the 17th century, mathematics has been an indispensable adjunct to the physical sciences and technology, and in more recent time, it has assumed a similar role in the quantitative aspects of the life sciences. Egyptian mathematics. Ancient Egyptian mathematics is the mathematics that was developed and used in ancient Egypt from the Old Kingdom of Egypt until roughly the beginning of Hellenistic Egypt. The ancient Egyptians utilized a numeral system for counting and solving written mathematical problems, often involving multiplication and fractions. The history of Egyptian mathematics is based on the extant original documents written by scribes, although in the case of Egypt these documents are few. They are all of a type and leave little doubt that Egyptian mathematics was, on the whole, elementary and profoundly practical in its orientation. The introduction of writing in Egypt in the pre dynastic period brought with it the formation of special class of literate professionals, the scribes. By virtue of their writing skills, the scribes took on all the duties of a civil service, record keeping, tax accounting, and the management of public works, building projects, and the like. Even the prosecution of war through overseeing military supplies and payrolls. Henry Rind invented Egyptian civilization. Here is the picture of Henry Rind attached on the left hand side. Moving on to the Mesopotamian mathematics. For Mesopotamian mathematics, on the other hand, there are a larger number of clay tablets which reveal mathematical achievements of a much higher order than those of Egyptians. The tablets indicate that the Mesopotamians had a great deal of remarkable mathematical knowledge, although they offer no evidence that this knowledge was organized into a deductive system. Further research may reveal more about the early development of mathematics in Mesopotamia or about its influence on Greek mathematics, but it seems likely that this picture of Mesopotamian mathematics will stand. I have attached a picture of a clay tablet on the right hand side belonging to the Mesopotamian period. The recovery of Mesopotamian mathematics was pioneered in the early 30s by Otto Neugebauer, an eminent member of the Institute for Advanced Study, whose association with the institute spanned 45 years. Neugebauer began his career as a mathematician in Göttingen. After fleeing Nazi Germany, he emigrated to the United States and became a major figure in the history of ancient mathematics and astronomy. Moving on to the Greek mathematics. Origin of Greek mathematics. The origin of Greek mathematics is not well documented. The earliest advanced civilizations in Greek and in Europe were the Minoan and later Mycenaean civilizations, both of which flourished during the second millennium BC. While these civilizations possessed writing and were capable of advanced engineering, including four-story palaces with drainage and beehive tombs, they left behind no mathematical documents. Though no direct evidence is available, it is generally thought that the neighboring Babylonian and Egyptian civilizations had an influence on the younger Greek tradition. Between 800 BC and 600 BC, Greek mathematics were generally lagged behind Greek literature, and very little is known about Greek mathematics from this period, nearly all of which was passed down through later authors beginning in the mid 4th century BC. Greek mathematics constitutes an important period in the history of mathematics, fundamental in respect of geometry and for the idea of formal proof. Greek mathematics also contributed importantly to ideas on number theory, mathematical analysis, applied mathematics, and at times approached close to integral calculus. Euclid collected the mathematical knowledge of his age in the Elements, a canon of geometry and elementary number theory for many centuries. The most characteristic product of Greek mathematics may be the theory of conic sections, which was largely developed in the Hellenistic period. The methods used made no explicit use of algebra nor trigonometry. An illustration of Euclid's proof of the Pythagoras theorem is given on the right hand side. List of ancient Greek mathematicians: Archimedes, Aristotle, Democritus, Diophantus, Euclid, Hippocrates, Pythagoras, Thales. I have added the picture of each one of them on the right hand side. Numeral system. Numeral system, any of various sets of symbols and the rules for using them to represent numbers, which are used to express how many objects are in a given set. Thus, the idea of oneness can be represented by the Roman numeral I, by the Greek letter alpha, the first letter used as numeral, by the Hebrew letter aleph, the first letter used as a numeral, or by the modern numeral 1, which is Hindu Arabic in origin. Here is the picture attached of a numeral system on the left hand side. Other examples of numeral system. The first one is Egyptian numeral system and the second one is Mesopotamian numeral system. Arithmetic operators. The four arithmetic operators were performed in the same way as in the modern decimal system, except that carrying occurred whenever a sum reached 60 rather than 10. Multiplication was facilitated by means of tables. One typical tablet lists the multiples of a number by 1, 2, 3, 19, 20, 30, 40, and 50, and so on. To multiply two numbers several places long, the scribe first broke the problem down into several multiplications, each by a one place number, and then looked up the value of each product in the appropriate tables. This is a picture of an interesting tablet in the collection of York University shows a square with its diagonals. The scribe thus appears to have known an equivalent of a familiar long method of finding square roots. Here is a picture attached on the right hand side of that particular tablet. The scribe recognized that the area of the circle is proportional to the square of the diameter and assumed for the constant of proportionality, that is pi by 4, the value 64 divided by 81. This is a rather good estimate, being about 0.6% too large. It is not as close, however, as the now common estimate of 3 1 by 7, first proposed by Archimedes, which is only about 0.04% too large. But there is nothing in the papyri indicating that the scribes were aware that this rule was only approximate rather than exact. Here is a picture attached on the left hand side where they have divided a circle into 7 squares, and then they have calculated the area of the squares, which approximately, and added the area of the four rectangles, right angle triangles to it, which approximately equals the area of square. A remarkable result is the rule for the volume of truncated pyramid. The scribe assumes the height to be 6, the base to be square of side 4, and the top a square of side 2. He multiplies one third the height times 28, finding the volume to be 56. Here 28 is computed from 2 into 2 plus 2 into 4 plus 4 into 4. Since this is correct, it can be assumed that the scribe also knew the general rule, that is a is equal to h by 3 a square plus ab plus b square. However, the scribe actually derived the rule is a matter for debate, but it is reasonable to suppose that they were aware of the related rules, such as that for the height of the pyramid, one third the height times the area of the base. The Egyptians employed the equivalent of similar triangles to measure distances. For instance, the second of a pyramid is stated as the number of palms in the horizontal corresponding to a rise of 1 cubit, 7 palms. Thus, if the second is 5 1 by 4 and the base is 140 cubits, the height becomes 93 1 by 3 cubits. The Greek Sale Thales of Miletus, 6th century BCE, is said to have measured the height of pyramids by means of their shadows. The report derives from the Hieronymus, a disciple of Aristotle in the 4th century BC. On the left hand side is a picture attached of Greeks measuring the heights of pyramids by shadows. Moving on to Hindu Arabic. Hindu Arabic numerals set of 10 symbols 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 that represent numbers in the decimal number system. They originated in India in the 6th or 7th century and were introduced to Europe through the writings of Middle Eastern mathematicians, especially Al Khwarizmi and Al Kindi, about the 12th century. They represented a profound break with previous methods of counting, such as the abacus, and paved the way for the development of algebra. Here is the picture added of the ancient Hindu Arabic numerals, and on the right hand side is shown is the picture of the abacus, which was one of the previous methods of counting. This is the picture of the evolution of Hindu Arabic numerals. The first picture is Brahmani, which was introduced in 1st century CE. Then it starts evolving and it keeps on evolving and evolving, and then it finally reached to the modern Hindu Arabic numerals. History. It was invented between the 1st and the 4th centuries by the Indian mathematicians. The system was adopted in Arabic mathematics, also called Islamic mathematics, by the 9th century. Influential were the books of Al Khwarizmi and Al Kindi. The system later spread to the medieval Europe by the High Middle Ages. The top one is the picture of Al Khwarizmi, and this bottom one is the picture of Al Kindi. These are the two books of the Al Kindi and the Al Khwarizmi. The first book of Al Kindi is the 40 chapters of Al Kindi, which include horary and astronomy, and the second book of Al Khwarizmi is related to the beginnings of algebra. The Hindu Arabic numeral system or Indo Arabic numeral system, also called the Arabic numeral system or Hindu numeral system, is a positional decimal numeral system and is the most common system for the symbolic representation of numbers in the world. The system is based upon 10, originally 9 glyphs. The symbol or the glyphs used to represent the system are in principle independent of the system itself. The glyphs in actual use are descended from Brahmani numerals and have split into various typographical variants since the Middle Ages. These system sets can be divided into three main families: Western Arabic numerals used in the Greater Maghreb and in Europe, Eastern Arabic numerals, also called Indic numerals, used in the Middle East, and The Indian numerals in various scripts used in the Indian subcontinent. The first one is the European, which is the Western Arabic numerals. The second one is the Arabic Indic, which lies somewhere between the Western and the Eastern Arabic. The third is the Eastern Arabic Indic, and the fourth and fifth one, Devanagari and Tamil one, they belong to the Indian subcontinent, and these are Indian numerals. Etymology. The Hindu Arabic or Indo Arabic numerals were invented by mathematicians in India. Persian and Arabic mathematicians called them Hindu numerals, where Hindu meant Indian. Later, they came to be called Arabic numerals in Europe because they were introduced to the West by Arab merchants. Positional notation. The Hindu Arabic system is designed for positional notation in the decimal system. In a more developed form, positional notation also uses a decimal marker, at first a mark over the ones digit, but now more usually a decimal point or a decimal comma, which separates the ones place from the tens place, and also a symbol for these digits recur ad infinitum. In modern usage, this latter symbol is usually a vinculum, a horizontal line placed over the repeating digits. In this more developed form, the numeral system can symbolize any rational number using only 13 symbols: the tens digit, decimal marker, vinculum, and a pre-painted minus digit to indicate a negative number. Now, moving on to the history of negative numbers. Negative numbers appeared for the first time in the history in the 9 chapters of the mathematical art, which is its present forms, dates from the period of the Chinese Han Dynasty 202 BC to AD 220, but may well contain much older material. Louis Hui established the rules for adding and subtracting the negative numbers. By the 7th century, Indian mathematicians such as Brahmagupta were describing the use of negative numbers. Here is the picture attached of the Louis Hui, and the book The 9 Chapters on the Mathematical Arts are present on the left hand side. Islamic mathematicians further developed the rules of subtracting and multiplying negative numbers and solved problems with negative coefficients. Western mathematicians accepted the idea of negative numbers around the middle of the 19th century. Prior to the concept of negative numbers, mathematicians such as Diophantus considered negative solutions to problems false, and equations requiring negative solutions were described as absurd. Some mathematicians, like Leibniz, who lived from 1646 to 1716, agreed that the negative numbers were invalid, but he still used them in calculations. On the left hand side, I've added two pictures. The first one is of Leibniz, and the second one is of Diophantus. Now we're gonna discuss the everyday uses of negative numbers. Temperatures which are colder than 0 degrees Celsius are represented using negative numbers. Similarly, latitudes which are south to the equator and longitudes which are west of the prime meridian. Electrical circuits. When a battery is connected in reverse polarity, the voltage applied is said to be the opposite of its rated voltage. For example, a 6-volt battery connected in reverse applies a voltage of minus 6 volt. Ions have a positive or negative electrical charge. Net run rate in cricket. On the right hand side, I have added a picture of all the longitudes along with the prime meridian. Here it is shown that the longitudes to the left of prime meridian are shown in negative sign. Then comes our next topic, which is invention of zero. Aryabhat is the first of the great astronomers of the classical age of India. He was born in 476 AD in Ashmaka but later lived in Kusumapura, which his commentator Bhaskara 629 AD identifies with Patalputra, modern Patna. Aryabhat gave the world the digit zero, for which he became immortal. On the left hand side, I have added the image of Aryabhatta. History related to the invention of zero. Christian Maculin timeline shows the development of zero throughout the world. The first recorded zero appeared in Mesopotamia around 3 BC. The Mayans invented it independently circa 4 AD. It was later devised in India in the mid 5th century, spread to Cambodia near the end of the 7th century, and into China and the Islamic countries at the end of the 8th. Zero reached the Western Europe in the 12th century. The zero was originally invented so as to give mathematical expression to something which we call nullness. Number line. After the invention of negative numbers and zero, there comes the invention of number line. The first mention of the number line used for operation purposes is found in Johann Wallis' Treatise of Algebra. In his treatise, Wallis described addition and subtraction on a number line in terms of moving forward and backward under the metaphor of a person walking. On the left hand side, I have added a picture of Johann Wallis' The Treatise of Algebra. Number line. In elementary mathematics, a number line is a picture of a graduated straight line that serves as abstraction for real numbers, denoted by the picture which is shown below. Every point of a number line is assumed to correspond to a real number, and every real number to a point. The integers are often shown as specially marked points, evenly spaced on a line. Although this image only shows integers from -5 to 5, the line includes all real numbers continuing forever in each direction and also numbers that lie between the integers. It is often used as an aid in teaching simple addition and subtraction, especially involving number line negative numbers. Now comes the next topic, which is development of algebra. Algebra. branch of mathematics in which arithmetical operations and formal manipulations are applied to abstract symbols rather than specific numbers. The notion that there exists such a distinct subdiscipline of mathematics as well as the term algebra to denote it resulted from a slow historical development. This article presents that history tracing the evolution over time of the concept of the equation, number systems, symbols for conveying and manipulating mathematical statements, and the modern abstract structural view of algebra. Role of the Pythagoras in the development of algebra. A major milestone of Greek mathematics was the discovery by the Pythagoras around 430 BC that not all lengths are commensurable, that is, measurable by a common unit. The Pythagoreans knew that for a unit square, that is, a square whose sides have a length of 1, the length of diagonal must be square root of 2, owing to the Pythagorean theorem which states that the square on the diagonal of a triangle must equal the sum of the squares on the other two sides. That is, a square plus b square is equal to c square. Role of Diophantus in the development of algebra. A somewhat different and idiosyncratic orientation to solving mathematical problems can be found in the work of a later Greek, Diophantus of Alexandria, who developed original methods for solving problems that, in retrospect, may be seen as linear or quadratic equations. Yet, even Diophantus, in line with the basic Greek conception of mathematics, considered only positive rational solutions. He called a problem absurd whose only solution were negative numbers. Diophantus solved specific problems using ADHOC methods convenient for the problem at hand, but he did not provide general solutions. Here is a picture of the book of the Diophantus attached on the right hand side of the slide. The fundamental theorem of algebra. Descartes' work was the start of the transformation of polynomials into the autonomous object of intrinsic mathematical interest. To a large extent, algebra became identified with the theory of polynomials, a clear notion of a polynomial equation, together with the existing techniques for solving some of them, allowed coherent and systematic reformulations of many questions that had previously been dealt with in a haphazard fashion. Here is the picture attached of Descartes on the right hand side of the slide. High on the agenda remained the problem of finding general algebraic solutions for equations of degree higher than 4. Closely related to this was the question of the kinds of number that should count as legitimate solutions or roots of the equations. Attempts to deal with these two important problems forced mathematicians to realize the centrality of another pressing question, namely the number of solutions for a given polynomial equation. Here On the right hand side is the picture attached of the Descartes rules of science. If fx is a polynomial function with real coefficients, then the number of positive real zeros is equal to the number of variations in the sign of fx or less by some even number. The number of negative real zeros is equal to the number of variations in sign of f of negative x or less by some even number. Moving on, roots of equations. We are familiar with the quadratic formula, the opposite of b plus minus the square root of b squared minus 4ac all divided by 2a. This formula allows you to find the roots of the quadratic equations of the form ax square plus bx plus c equals 0. Where does this formula come from? Why did older civilizations need to solve questions of this form in the first place? This is the quadratic formula as it is taught to most of us in school. x1 comma x2 equal to minus b by 2a plus minus under root of b square minus 4ac upon 2a gives the solution to a generic quadratic equation of the form ax square plus bx plus c equal to 0. On the right hand side it's shown about the value of d, how it affects the solutions. If d greater than 0, we know it will be two real solutions, d equal to 0, one real solution, and d less than 0, complex solutions. The development or derivation of this mathematical idea is usually as logical, deducible, and rectilinear as possible. This brings about the common notion that its historical development is similarly as continuous, logical, and rectilinear. One mathematician picking up an idea where another mathematician left it. Using the quadratic formula as an example, it will be shown that the historical development of mathematics is not at all rectilinear. Instead, parallel developments, interconnections, and confluences can be found, which, to complicate this stuff even further, are also interrelated with social, cultural, political, and religious matters. The so called quadratic formula has been derived in the course of a few millennia to its current form, which is taught to most of us in school. This entry will strictly concentrate on the historical development of the quadratic formula. Some mathematical background may be of use to fully understand the described development. However, the mathematics used in this entry will be kept at a necessary minimum. The beginnings is done by Egypt at around 1500 BC. The first aspect that finally led to the quadratic equation was the recognition that it is connected to a very pragmatic problem, which in its turn demanded a quick and dirty solution. We have to note in this context that Egyptians' mathematics did not know equations and numbers like we know nowadays. It is instead descriptive, rhetorical, and sometimes very hard to follow. It is known that the Egyptian wise men, engineers, scribes, and priests were aware of this shortcoming, but they came up with the way to circumvent this problem. Instead of learning an operation or a formula that could calculate the sides from the area, they calculated the area for all possible sides and shapes of squares and rectangles and made a lookup table. This method works much like we learn the publication tables by heart in school instead of doing the operation proper. I would like to end my presentation with the quote: "The laws of nature are but the mathematical thoughts of God, which we all are trying to understand." This is written by Euclid, one of the famous Greek mathematician. Thank you. My name is Rupam Gumber. Enrollment number is 2031 2028, and my branch is Applied Mathematics. Thank you.